Welcome back to ECE 441A, 541A. Have special office hours today if that's of interest, but those are the normal Wednesday times from 12:30 to 2:30, just to get us ready since we have our third exam this Friday. And the third exam will be covering material on homework 6 and 7, which is the root locus material. Homework 7 is dealing with trying to design controllers based on the root locus technique, or how do we place poles and zeros onto the complex plane to move or shift the root locus around. And we're shifting it around to try to make it pass through our desired locations or points to achieve our design specifications. If you're in 541, deliverables 1, 2, and 3 have different dates, but the main one is deliverable number 2 is due on the 7th or the last day of class. Today what I want to do is actually talk about designing a controller for our mass spring damper system, which is lab number 3. And there's already notes for that, there's already a video for that, and I think you need to watch those, but I want to give you and look at those, but I want to give us another system with which to explore this idea of plotting root loci and then trying to shift that root locus around by introducing additional poles and zeros. And we'll step through that or evolve that process from a pure gain controller to a phase lead controller and then into a PID controller. And the PID controller, the reason why it's a PID and not a PID is because it's standing for a proportional integral derivative, and you can see those three terms in the transfer function of the controller G sub C of S. We have the proportional piece, we have an integral piece, and we have a derivative piece. Actually, this is an ideal transfer function. In reality, we would put a fast pole underneath that derivative term so that we don't have the gain going off to infinity as the frequency increases. That we don't want. We don't want to keep increasing the gain at high frequencies where we might have a lot of noise. And in that sense, we need to at least stop that progression of the K sub ds, and I keep indicating my hands or talking with my hands, but when we have an S, if you looked at the Bode plot for that S, what would that look like? If we just had a derivative, a pure derivative, or a zero at the origin, what would that look like in a Bode plot sketch? It's plus 20 dB per decade all the time, isn't it? It's just going up and up and up and up as we get higher and higher frequencies, and we probably don't want that, which is why in reality we have this fast pole introduced into our derivative term. But let me erase that virtually because we won't play with what I just erased in this class. We'll assume that that pole is really fast and it won't influence our design technique or our design strategy. But just be forewarned that in fact that pole needs to be there. You don't want to be having derivative action for really high frequencies. That's just going to make your noise or anything else in high frequencies that much worse, and that's not what we want. If we have time, we'll talk about designing controllers to stabilize unstable systems. And here I tried to really drive home the point that you do not want to cancel unstable poles and zeros. You don't want to cancel something in the right half plane with a pole or a zero, but placing poles and zeros in the right half plane is allowed. Can that be any more confusing? But it will hopefully be made clear as we go through these examples. Let's look at a typical in quotes, in air quotes, mass spring damper system. Your particular system may not look quite like this, but it should look something like this. It might have a numerator piece that's maybe about 5,000, and the denominator, we have 2 poles, and they might be in the ballpark of having a real part of -2 and imaginary part of around 20, plus and minus J20. That's, let's say, a hypothetical or a typical mass spring damper system in the lab, and now I've already given you the answer in terms of these questions. Where are the poles located in this mass spring damper system? The way that I factored it in the rightmost expression should make that come screaming out at you. The poles are at -2 plus and minus J20. Since I've written it as S plus sigma quantity squared plus omega sub d squared, that's exactly where our poles are located. And then I've actually factored the numerator in such a way that if I set S equal to 0, something else pops out, and that something else is our DC gain. And the DC gain in this particular system is 12.3. What we want to look at now is what happens if we kick this system and then try to control the system. In the first lab, you simply kicked the system. You hit it with a step and watched it shake. And then you removed the step and it shook again, and you kicked it again and it shook again 3 different times, and you could have looked at those 3 times, but probably you just looked at one of those particular options. Now, for this particular system, if we look at the open loop behavior, what would you see based on this information that's already presented to us? What could you determine from this information? What kind of performance specifications are immediately available to us from what I've given already about that mass spring damper system in the form of a transfer function? You know the poles. What can you tell me once you know the poles? You can say whether it's stable or not. That's a very big picture view. Is this system stable? Yes, the poles are in the left half plane. Can you tell me anything about how those systems decay with time? Can you see, when you examine those poles, do you see a time domain expression coming out of those poles? Do you see an e to the minus sigma t times a cosine omega sub dt plus a sine omega sub dt term? That's really what you have when you kick this system. And if you have that system and you kick it, what is the sigma? You have e to the minus sigma t. What is sigma in this case? 2. And what is sigma good for in terms of a performance spec? The settling time. So if we looked at the 2% settling time, that's going to be 4 tau, or 4 over sigma, which in this case is now, getting ahead of myself, I'm wanting to give the answer. It's now 2 seconds. What else can you say concerning those pole locations? You could do the percent overshoot. You could even do the time to peak, couldn't you? Because you have omega sub d. Let's look at the percent overshoot. If we want the percent overshoot, we need to find the angle. The angle, now that I've scrolled it off the screen, is the inverse tangent of 20 over 2, which actually ends up being 84.3 degrees. Pretty big angle. And if you now looked at the zeta value for that angle by taking the cosine of theta, that turns out to be 0.1. And now we can use figure 5.7, which is just happening to be somewhere in your crib sheet. And now that we know that we have a zeta of 0.1, what's the percent overshoot? It's a little bit more than 70, isn't it? 72, 73. We're dealing with that curve, and we read straight up from 0.1, and we now see that we have a 72 or 73% overshoot for that system. If we just kick it and let it go without any kind of control, it will have quite an overshoot. Whoops. So from this, we find that the percent overshoot, if we simply eyeball it, is 73%. Question. What was sigma? So this is now, if we look at this, this is my minus sigma plus and minus j omega sub d in that parameterized form. And I wrote this as an s plus sigma squared plus omega sub d squared. I factored that denominator so that I explicitly have the real part identified and the imaginary part identified. And that's where they come from in those poles. What if we now apply a controller? We now have our system modeled as a two-pole system with a numerator, a constant numerator. Let's now put a controller in there. But in contrast to what we did in lab number 2, now we aren't going to say that we have everything available to us to feed back. In lab number 2, we had position and velocity available to us, and we could then scale those and feed those back. What I want to do now is restrict that and say the only signal that we can measure now is the position, and feed that back and then kick it. And for starters, let's see if we can now examine what happens with a pure gain controller. Or G sub C of S is equal to K. What design strategy do we now have available to us? We could sketch the root locus for this. Because we have the plant, we can sketch the poles and zeros of that plant, and this is in our standard form. We can now see what happens as we adjust K from 0 to infinity. That's how our closed loop poles will move in a pure gain feedback configuration. And what do we have? In our system, this is obviously not drawn to scale, so the angles are going to be not correct, but we have poles at -2 plus and minus J20. What's the root locus of this when we have a gain K, a pure gain controller? What's the root locus of this going to look like? How many pieces of bread do we have? How many times have I sliced that loaf of infinitely long bread? Now I'm getting hungry. I haven't cut it at all, have I? I don't have any poles and zeros on the real axis. So I just have one big piece of bread. Is that on the root locus? If I looked at any point on this root locus, on the real axis, have to wake up, it's Monday. If I looked at this point and I said, what's the phase angle at that point? You would say, well, due to the poles and zeros, you would say, I can find the angle to that point from this pole, and it's that angle. It would be negative, I don't know, minus 120. And this angle would be, let's say, plus 120. I sum those up. I now take, I don't have any zeros, so I don't have an angle due to the zeros, and I take minus the top angle, minus 120, plus the bottom angle, 120. I have 0 degrees. Is that equal to what it needs to be on the root locus? No, it needs to be minus 180 degrees, and it's at 0 degrees. And if I looked at any point on that real line, none of those are going to have an angle of minus 180 degrees. I do not have any part of the real axis on this root locus. The root locus never is on the real line for this pure gain controlled system. But what does the root locus? Where is it going to be, or what happens? So now we've already done Rule 1, Rule 2, Rule 3. You have these cheat sheets available to you. You go, okay, what are my asymptotes? Do I have any asymptotes, and when do I have interesting asymptotes? When I have a pole zero excess. Do I have a pole zero excess? What is it? 2. So now I divide 180 by 2 and I get 90. I now have 90 degrees for my fundamental angle, and my other one is 270 or minus 90. So I now have plus and minus 90 degrees. Where's the centroid of that asymptote located? Minus 2, minus nothing, divided by 2. It's at minus 2. So my asymptotes, I now know where they are. There's my asymptotes. Where do I start my root locus? On the open loop poles. Where do I end my root locus? As they approach the asymptotes. But in this case, I never leave those asymptotes. I start on them and I stay on them. In this case, my root locus looks like that. That's my root locus for a pure gain controlled system for this mass spring damper system. What's this tell us? What's our settling time? What's the 2% settling time? What's my sigma? 2. What was sigma before? 2. So has my settling time changed? No, I still have 2 seconds, don't I? And that's no matter what K is. I'm not going to speed up my system in that way. I'm not going to make the settling time any smaller. What about my percent overshoot? Hopefully you remember that this T sub C is kg over 1 plus kg. That's what I'm seeing, and now I have this denominator, and I found that I haven't changed the real part any. If I look at this T sub C, I now have, is it clear that it will actually be k over 1, s plus 2 squared plus 20 squared plus k. That's the closed loop transfer function, and there's my denominator. And what happened to the linear term in the denominator? It's not impacted by k at all, is it? It's still this s squared plus 4s plus 4 plus 400 plus k. Now I return, what's my percent overshoot? And now you can answer with the good answer. It depends, right? It depends on K. If you don't pick a K, you can't really answer that question. But if I pick a K, it's going to put my closed loop pole somewhere on that red line. And what's a K going to do in terms of the closed loop poles? What's K changing? It's not changing the real part, is it? It's changing the imaginary part. And what happens when I change the imaginary part? What is that? That's omega sub d, isn't it? So what's happening? Now if I put this system, this plant that you have over in the lab, in a pure gain feedback configuration with output feedback, and you crank up that gain K, it's just going to shake quicker and quicker as you crank up the gain K, isn't it? But it will still settle at the same amount of time. It'll still settle in 2 seconds. But boy, will it shake prior to those 2 seconds. It will shake at a frequency determined by omega sub d, which is impacted by K. In this case, for this system, a pure gain output feedback controller is probably not what you want, is it? You probably don't want to make this guy just shake a little bit more. Maybe you do. Maybe there's a stop button. If that happens, hit the stop button. I don't want you breaking the equipment. But you can make it shake by this technique. What if we put in a K equal to 0.1 just for grins? Then, oh, and you know what I forgot to do? You guys didn't wake me up sufficiently. My numerator piece should have still been here, which was approximately 4,000, wasn't it? 49.69. So for a nominal amount of 49.69, that sounded like a price to me, but anyway, we now have 49.69 scaling K in the denominator. It's still the same thought process. K is still changing omega sub d, or the natural frequency. If we put a K of 0.1, then the denominator becomes s plus 2 squared plus 20 squared plus about 490, right? Or if you look at this, you now have the s squared, or s plus 2 squared plus something a little bit bigger than 20. Now it's actually at almost 30 for omega sub d. And you could figure the theta, the angle now is bigger, the zeta is smaller, and the percent overshoot is even bigger. Now for this particular case, the theta would be, if I did my math right, do I even have it, 86 degrees. Zeta now is 0.067, which is even further, and they didn't even plot that in figure 5.1 really. And now you have a percent overshoot of 81% versus 73%. So this isn't going to help us if we wanted to speed up our response. Let's now think about speeding up the response. We are wanting to change dramatically the root locus shape. We don't like this original shape that just goes up and makes the system shake more, faster, without changing the settling time. So if we want to change the shape of the root locus or speed up the response, speeding up the response means bend that root locus over. What do we need? What kind of controller is possible that we already talked about? A phase lead. Before we even get to a phase lead, let's do a thought experiment. These are what you like, right? The reason this is a thought experiment is because we really don't want to do this in practice, but it gives us something to think about. We started with our poles here, and suppose that I put in just a 0. Here's the thought experiment. I'm going to adding only a 0. The reason it's a thought experiment is because we can't just add a 0. That's a pure derivative, and we don't want to have a pure derivative. But this gives us an idea, or helps us start thinking about what putting poles and zeros into the S-plane might help us do. So we're looking to help our insight. What happens now, if I gave you this Friday, could you sketch the root locus? Now how many pieces of bread do you have? Now we have 2, don't we? We've cut it where that 0 is. Is the segment of the real line to the right of that 0 on the root locus? No. What about to the left of that 0? What's my asymptote? What's my pole 0 excess for this hypothetical thought experiment? 1. So what's my angle? 180. Does it matter where the centroid is? No. I'm just going off to minus infinity. So one pole goes to the 0, and one goes off to minus infinity. And how do they get there? How many branches do you have? How many closed loop poles do you have? 2, because you had 2 open loop poles. So you have 2 closed loop poles. You have 2 branches that start on those 2 x's on the open loop poles, and they have to eventually end up one going to the 0 from the left and one going to minus infinity. So these, it doesn't really matter. Let's just do this. We're just thinking, but they have to somehow come to the real line. One branch will go to the right, one will go to the left. And they meet where? If you needed to find that point, how would you find it? Where they come into the real line. Trying to not say the word, but they're re-entering the real line. That's a re-entry point. That would be a relative minimum of your gain value from the magnitude condition. Another way to use some of these rules. Well, now that we have this insight, we know we can't just plop a 0 down. We have to plop a pole down also. But if we plopped a pole down to the left, we would still have something like this shape. We would be pulling those branches further into the left half plane. And what does that do? That gives us a better settling time. That's what we were trying to accomplish. So if we come back to reality a little bit with a phase lead controller, the phase lead controller says, oh, let's put a 0 and a pole. And we now are trying to determine where we want those. And we now have G sub C is K S plus Z sub C over S plus P sub C. And in the lab, you're going to have to make some decisions. You're going to maybe need to accomplish a particular settling time. But maybe I don't say anything about the percent overshoot. But if I say a settling time, what are you seeing on that S-plane? If I say settling time, you're seeing a vertical line. And now you want your branches to be to the left of that, and then you'll find a gain to get you on those 2 branches somewhere to the left of that vertical line. That vertical line would then be determined by your settling time specification. And now, what's going to happen? Well, you could have all sorts of pictures depending on the separation of the pole and the zero. But probably what's going to happen is these will go this way towards the asymptote, and this one will come in here. Right? So you're trying to locate that asymptote far enough to the left to achieve your settling time specification. And then you would pick closed loop poles to meet your settling time spec. So let's now say this is sigma sub A, and this is the settling time spec. So we have all sorts of lines flying around, but we need to keep them straight and understand how they might help us in this design process. What will you do in the lab? Well, you'll actually start building this up, and I actually give you a program, a script in MATLAB that you can punch numbers in, and it will start walking you through this phase lead controller design approach. In this case, we have our transfer function, we have a settling time, we have now a step response, and somewhere down here is figure 1. Does that sort of look like your system? Maybe. Did yours ring that much in the lab? No, it didn't ring that much. Why did yours not ring, and why did this one ring so long? What could be causing that? This is ideal. What's in the lab? Reality. Why is it maybe not ringing so much? Friction that we didn't model necessarily. And so in the lab, you have maybe after you hit 1 or 2 humps, maybe if you have a weak spring, you only get 1 hump. The momentum isn't enough to carry you on as this ideal linear system behavior would demonstrate. In the lab, the friction and the things we aren't necessarily modeling kind of dominate, and now you have just 1 or 2 humps before you settle. So the theoretical settling time might be longer than what you see in the lab. So if you calculate and you say, oh, I need a settling time of 4 seconds, and you do all your analysis and you go to the lab and you get a settling time of 3 seconds, you go, uh-oh, something's wrong. Well, maybe not. Maybe it's just reality that's now coming up to show itself and saying, you lucked out. Now reality is helping you in that particular specification, because the momentum wasn't there really to overcome some of those natural or physical parts of the system that we aren't modeling in this ideal 2-pole behavior. So we want to somehow adjust for that. Where do I want to go? So that was the open loop. Then what I have provided is something called P-lead, a question. So we didn't increase the settling time, we decreased the settling. When we decreased the settling time, we were putting that 0 in there to try to pull the branches of the root locus over into the left half plane further, and that was helping improve our settling time. So if the question is, repeat the question again. So now you're wanting to slide your 0 a little bit closer to the imaginary axis. And what happens if you slide your 0 closer to the imaginary axis? Is that the question? So now you're decreasing your settling time. Those curves or those poles will come over, but you'll have to now play with your asymptote formula to determine how do I pick my controller pole and my controller zero to make that asymptote centroid locate it where I want it to be located to achieve my settling time specification. Now, what we have seen maybe in the first part of the last lecture is that the more zeros we have, the more they really kind of mess with our percent overshoot. They make it worse. So we really don't want to just load up on zeros and make those close to the imaginary axis. Those will deteriorate our pure two-pole system behavior that we've come to grow and love in figure 5.7. That gets kind of thrown out the window. And so now that's just a crude rule of thumb to worry about. But if we now go back and we start playing with P lead, we put in our plant, and now we plop down. It will ask you, select a point, and now you'll get a cursor in your MATLAB script, and you'll now need to locate a point in the complex plane, which is really what I'm doing right there. I'm clicking on that point. I'm locating my cursor on the root locus somewhere to the left of where I want to be to meet the settling time spec, and I hit my mouse button. Then MATLAB returns a number that actually says, oh, you've now picked closed loop poles at -10 plus and minus J50. Not a great angle, is it? But it is quite far relative to -2. It's now -10. So we have improved our settling time. If we cut to the chase and just slide down to picture 2, there's the root locus, and where that cross is where I tried to find the spot that I was after, and I think I wanted to be to the left of -8, and it looks like I was. And do I have, that's now my response. And look at the horizontal axis. What's my time axis? Before I was settling maybe at 2.5 seconds or 2 seconds. Now I'm settling at 0.6. I think the spec in the lab is to have a settling time of 1/2 of a second. And this seems to be doing that. I couldn't do it with a pure gain controller. Now I was able to do it with a phase lead, but maybe we're not happy with this. What's my steady state error in this simulation? Maybe you missed it. You should be paying really close attention, but I put in a step of 2,000. So that's where I'm trying to go. I'm trying to get to 2,000. Where did I go? Did I get close? Define close. Right? It's not very close, is it? I made it up a little bit above 1,000. So I have quite a big steady state error. Maybe I don't like that. You go in and you lay this on your boss's desk and she goes, "What are you doing? Are you being funny? I told you to control this system, and you made it go to 1,000 or 1,200, and I want it to go to 2,000. So you leave her office and you go back to your desk and you go PID. No, you go PID, really the I part, right? The I part, you want to put in an integrator to try to reduce that steady state error. That integrator is going to integrate away that error and drive your final value to lock on to where you reference it. Question? So does that always mean that you need an integrator term when you're introducing a derivative term? And the generic answer is no. It depends on your specification. But in this particular case, if steady state accuracy is important to us, we may need the integrator piece. But in some systems, you may not be that worried about your steady state accuracy and more about your transient behavior. And in that case, you may just want a phase lead controller without a pure integrator. The question was, if you only enter a derivative term, it will dramatically change your, or increase your steady state error. Probably it will deteriorate your steady state error, but it really does depend on the system. Yes, so this is all we've done is entered a 0 and a pole. That's what these blue pieces are. Well, there's a lot of blue pieces, but the 0 we put in and the pole we put in. So yes, so let's go to the next question, which is, I hope, going to be talked about now, is what happens when we introduce a PI controller or a PID controller. If we just did a PI controller, this gives us now a G sub C, which is now K sub P plus K sub I over S. And if we put that over a common denominator, we have a 0 and a pole. But now the pole is locked at the origin, and the flexibility that we have is adjusting the zero's location. So now we flipped the direction or the orientation of our pole-zero combination. Now we have the pole to the right of our 0. In the phase lead, we had our 0 to the right of our pole. But let's go a little bit further and let's do a PID controller. But you could now design this. You have now two parameters to adjust. The K sub P and K sub I can now locate that 0 and the gain in that controller. If you factored this out, you would now have K sub P times S plus K sub I over K sub P over S, so that now you have a pole right at the origin, so P sub C is 0, and you have a 0, Z sub C, that's defined by K sub I over K sub P, and you have the adjustable gain K sub P. Let's do this same idea, but let's also introduce an additional piece, which is the derivative piece. And the reason we want this is for that integrator piece. And the derivative piece just helps us change the transient behavior a little bit more. If we now have G sub C of S, that's now K sub P plus K sub I over S plus K sub D S. Or if we put all of that over a common denominator of S, you see that the K sub D term will be S squared, and that will be our highest power in the numerator. Then we factor other pieces out, and we have a K sub P over K sub D S plus a K sub I over K sub D. And as I said before, this is really a hypothetical. We would probably have had this over some fast pole, and so we would have that fast pole, and that just makes things a little more messy, so we are neglecting that in our discussion. So let's not do that in this class. We'll just neglect what I've highlighted in yellow. That's not highlighting now, that's erasing. Okay, so now put on your virtual imaging devices, and now you've erased what's shaded. It's not highlighted, it's erased. Okay? Now that we have that, how many zeros do we have? What's the degree of my numerator? I have two zeros, all by the choice of K sub P and K sub I. K sub D will adjust the gain. So really, I have this structure for my PID controller. And what can I do now with Now do you see that I have a zero shaker and a pole shaker? My pole wasn't much of a design. It's plopped right on the origin. So that's fixed. But now I can put two zeros down in the complex S-plane. And you now get to use your creative juices to figure out where you want to put those zeros. What if somebody says, well, the pole was there, now I want to put two zeros there. What's the root locus going to look like for this pattern of poles and zeros in a PID controller? I have total, well, not total, but quite a bit of flexibility in selecting those zeros. Now I've picked them to be complex conjugate, so that my numerator would have those two red circles as factors. What would the root locus of this look like? How many pieces of bread do I have? 2. Which piece is on the root locus? The left piece. Whoops, that was supposed to be red. How many branches do I have? 3. I have 3 closed loop poles. So these will probably just do something nice. And you would then locate your closed loop poles to be there, there, and now this guy is maybe there. There would be your 3 closed loop poles. What if somebody said, oh, I don't want my zeros there, but instead I'm going to get fancy and put them there. So now I have minus z sub 1 and minus z sub 2. Now what's the root locus look like? How many pieces of bread do I have? 4. Which pieces are on the root locus? And now what do I do? What's my pole zero excess? One. I've changed basically the relative degree of my system, haven't I? Or my pole zero excess by putting 2 zeros in with 1 pole. So now I started with a pole zero excess of 2 in my original system. I've now made my life easier. Now I'm down to 1 pole zero excess, and I have an asymptote at minus 180 degrees, which means that one branch is going to go there, one is going to go off there, this one's going to go that way, and these two are going to come around, aren't they? And you have all these different possibilities. Now your closed loop poles, maybe you do it there, there, but one is going to be stuck between the origin and wherever you locate that minus z sub 1. And again, I give you a program somewhere to execute, PID. And you can enter your system, you can design your controller. I actually, in this case, it looks like I've put, where have I located my zeros? Minus 10 and minus 20. Similar to that most recent illustration. And if I now go down to one of these plots, there's what I just said might happen with our root locus. Do you see how I quickly drew that on the back of an envelope and MATLAB just confirmed it? Isn't it nice to have those skills now that you can just sketch these root loci? What if we did it a different way? I think I have a different figure here. Oh, now that's my response. Does that look better in terms of steady state accuracy? Yes. What about my percent overshoot? Not too bad. It's not ringing a lot. And that's what you'll be doing with this kind of design strategy in lab number 3, designing a phase lead controller and a PID controller. And we'll pick up with stabilizing unstable systems with possibly unstable controllers on the next time that we meet.